Hi everyone, so today we will be doing our final project presentation for the subject NET3204 distributed system. We are from group 28 and the group members involved are listed on the slides. This project focuses on the execution of scientific workflows, which are commonly used in modern research to process large datasets through multiple dependent tasks. As scientific experiments continue to grow in complexity and scale, running these workflows on a single machine becomes inefficient and often impractical. Distributed systems provide a solution by enabling tasks to be executed in parallel across multiple computing nodes, improving performance, scalability, and reliability. This project explores how a distributed platform can be designed and used to support such scientific workflows effectively. The main goal of this project is to design and deploy a distributed computing platform that can efficiently execute the montage scientific workflow. This goal focuses on assessing whether a distributed system can handle computational and data-intensive nature of astronomical image processing more effectively than a single machine approach. To support this goal, several objectives are defined. First, the project evaluates how distributed computing resources can improve workflow performance, particularly in terms of parallel execution and scalability. Second, the project demonstrates how workflow orchestration and distributed storage work together to manage task dependencies and large datasets. Finally, the project analyzes the suitability of distributed systems for real-world scientific workloads using montage as a representative and widely recognized scientific use case.
For our project, we implemented the montage scientific workflow. Montage is an astronomical engine used to create high-fidelity sky mosaics. It works with FITS images, otherwise known as Flexible Image Transport System, the standard format for telescope data. The most important thing to understand about montage is its precision. It doesn't just stitch together images, it preserves astrometric as well as photometric accuracy, ensuring every star's position and brightness remains scientifically valid. For researchers, this is the difference between a pretty picture and a usable piece of scientific data. Technically, montage is structured as a directed acyclic graph, otherwise known as DAG. It follows 5 main stages, from initial image discovery through to background rectification and final coaddition. This DAG structure defines the dependencies of our system. While the workflow is sequential, meaning we can't coad images before they are reprojected, it is also highly parallelizable. Stages like reprojection can be split across multiple nodes simultaneously. This makes montage the perfect use case for testing a distributed platform's ability to handle complex task dependencies. Our use case diagram, as shown here in this presentation slide, demonstrates how the researchers interact with the system. The user simply submits the dataset and configures the parameters. The platform then automates the entire pipeline. One of our key goals was ensuring that the user could monitor the workflow in real time. Instead of waiting blindly, the researcher can track job states as they move across the cluster, eventually retrieving the final mosaic once the system completes the execution. So why did we choose this for a distributed systems project? Because montage is computationally expensive. FITS files are large, requiring substantial storage, while reprojection involves intensive CPU coordinate shifts. On a single machine, these tasks create massive I/O bottlenecks. By distributing the workload across an AWS cluster using HD Condor, we effectively divided these tasks, improving resource utilization and speed. Ultimately, montage provided us with a real-world stress test. It forced us to solve practical problems in dependency resolution and data management across multiple nodes, proving our platform can handle genuine scientific collaborations rather than just synthetic benchmarks.
This demonstration shows the execution of the M100 astronomical mosaic workflow using the montage toolkit. automated via htcondo. All workflow data is stored on a NFS directory to ensure accessibility across compute nodes. So before running the workflow, I verify that the shared NFS storage is mounted. This ensures that all input data and output results are accessible to htcondo worker nodes. The M101 dataset consists of fits image stored in the raw directory. A predefined header file specifies the mosaic geometry, while separate directories are used for projection, differencing, and background corrected outputs. Stage 1 performs image reprojection using the montage module mProject execute. This step aligns all input images into a common coordinate system. The command is encapsulated within a wrapper script and submitted as a vanilla htconda job. Now I'm going to show the submission. The job is submitted to htcondo, which schedules execution on an available worker node. Progress and completion can be monitored using the condo queue. Now I'll be showing the result. As you can see, after completion, the projected image are returned to the shared storage, confirming such a successful execution of stage 1. Now I'll move to stage 2. So stage 2 performs background rectification by computing image overlaps, generating difference image, creating background planes, and applying bubble corrections. These dependent steps are bundled into a single htconda job to maintain execution order and data consistency. Now I'm ready to submit the job. So htcondo executes the background rectification pipeline as a batch job, producing corrected images and the final mosaic. Now with this, I'm going to show the final output. So the workflow produces both fits mosaic for scientists, analysis, and a PNG image for visualization. And that's all from my part, and I'll pass it on to my teammate.
Okay, hello. So I am taking part of the DACMAT montage workflow. So first we go to the directory which contains the raw fits image, the DAC workflow file, and the htconda submit files needed to run the pipeline. And then after that we check the DAC file using the cat montage DAC. So this DAC defines two main jobs, the project job and the background job. The project job performs image reprojection while the background job handles background modeling. The DAC ensures that the background job only runs after the project job has completed successfully. So now let's try to submit the workflow through the condo submit. Okay, so we submitted one job to the cluster 118, and now let's try to monitor it using condo queue. And as we can see here, one job submitted, and there is and it's on idling. And now we can try to check it again. Okay, so this time the job one job still remaining, but it moves from idling to running. And now we will use the tail/fm montage.dac.dacman out to see the log. Okay, so the log finished successfully, and now We can try with ls.lh.mo1.fis to see if the file is there, and it's there. And now we try to see how long it takes for time bash to output the same workflow as opposed to htcondor. Okay, so the result is out. As you can see, structure stat is okay, module mviewer, type grayscale, and now let's try to see the file with ls/lh mo1.png, and it's there. So we can see that it returned m101.png file. And now we can try to see how long it take with the grep time execute montage dot notes.log. So those are the results. And now I want to show it okay, so we can see there from time it takes about 24 seconds to finish. And now we go to the terminal to see the final output image, the mosaic image on the computer through terminal. So I'm just copy pasting the commands on my notes. Okay, it's downloading. Okay, the issue with the okay, that's because the file didn't exist in the folder. Okay, now let's try to do it again with ls.lh m101.png, so I can just directly show the output of the image. And there you go. So that is the output on the image that is submitted and executed on htcondor on the AWS instance. Thank you.
Hi, I'm Yiming, and I'll be sharing what we learned from this project, the challenge we faced, and how the system performed overall. One of the main lessons from this project is that a distributed system is not just about running multiple virtual machines. While AWS makes infrastructure provision easy, system reliability depends heavily on correct configuration of networking, storage, and scheduling components. We found that even small configuration errors like the restrictive security group rules, incorrect file permission, or wrong job path could completely stop the workflow. This highlighted the importance of validating the environment carefully before full deployment. Another important lesson was understanding the workload characteristic. The montage workflow includes highly parallel image reprojection tasks and also the memory-intensive background rectification stages. Allocating resources without considering these differences resulted in instability. By making resource allocation workload aware, the system became more stable and efficient. Finally, incremental testing played a critical role. Running the workflow in a smaller subset allowed us to detect issues early, improve reliability, and prevent large-scale failures during full execution. Several technical challenges were encountered during implementation. Initially, htcondor worker nodes failed to join the pool due to restrictive AWS Security Group's configurations. This was resolved by enabling the required HT condor and NFS ports for internet communication. Second, we also faced the NFS permission and ownership errors, where worker nodes could not write output files. This issue was caused by mismatched user group IDs and NFS root squash behavior. Standardizing UID and GID values and reconfiguring NFS exports resolved this problem. Another issue involved jobs entering the health state due to the missing log directories. Adding a pre-processing step to create all required directories before job submission prevents this error from recurring. This solution significantly improved workflow stability and reduced job failures. In conclusion, the project successfully executed the montage workflow on a stable and fully integrated AWS-based distributed platform using HT Condor for parallel processing. The final mosaic output was validated using visual inspection and fits metadata checks. After resolving system issues, all jobs completed successfully, and the platform demonstrated reliable execution across different workloads. For future improvement, replacing NFS with scalable storage such as AWS S3 with caching or a parallel file system would improve the I/O performance. Containerization using Docker or Singularity would standardize execution environments, while workflow engines like Pegasus or Nextflow would add fault tolerance, monitoring, and provenance tracking. This enhancement would allow the platform to scale to larger dataset and support more complex scientific workflows. That's all from our group. Thank you.